So today, so real numbers is everything, right? That's all the numbers out there? No, it is not. It is not. Turns out the real numbers are just a subset of an infinitely larger set called the set of complex numbers. That's what we're going to talk about today. But before we get there, we have to just define a few things. So when we've talked about square roots of negative numbers up to this point, we've always just said, well, there's no real solution if we're solving an equation, or it's a non-real number, and stopped, right? Well, we can go further if we define something called the imaginary unit. So the imaginary unit we write as a lowercase I, and that's always what that means. It is the number whose square is -1. In other words, I squared is equal to -1 by definition. So I is equal to the square root of -1. Okay, so then we're able to simplify something like this. The square root of -25, how could I deal with that? How could I split that up in a way then? If I know that I is equal to the square root of -1, what could I do here? Okay, yeah, I'm going to break it up into the square root of +25 times the square root of -1. And what's the square root of 25? 5. What's the square root of -1? I, exactly. And so our answer is 5i. Okay? And that is what we call an imaginary number, a pure imaginary number. And all the terminology will all make sense soon. But an imaginary number is just always represented as some real number times I. Okay? All right, so what about square root of -32? What's that going to be? I don't want to break it up into 8 and 4. I can have a bigger perfect square factor of 32 than 4. 16 and 2? Yeah. Good. So I'll split this up into, square root of 32 times square root of -1. And square root of 32, I'll break it up into square root of 16 times square root of 2. And what do I get then? So I get 4 times the square root of 2 times I, right? Okay. Now, sometimes we choose to write it like this, not for any mathematical reasons, because really this is the best way to write it. Because an imaginary number is always a real number times I. So that's written in the correct form, an imaginary number times I. But it's a little bit dangerous. How come? It's just a practical consideration. It has nothing to do with math. Say it again? Well, yeah, but what could you mistakenly, like if you're writing this out, what mistake could you easily make if you write it like this? Yeah, you might mistakenly put the I inside the radical, right? Or it might be difficult to tell if it's inside the radical. So for that reason only, sometimes we put the I in front of the radical, but in our minds, it's always after the radical. It's always the entire real number, 4 times the square root of 2 times I, even if we write it this way, right? Okay, so what do we see here? Well, we're seeing a pattern. Like there's a shortcut we can take. Anytime we have a negative number inside a square root, well, we just automatically know that the negative inside is going to become an I outside, right? So that's what we get. Very profound statement attributed to me. You could look at books of quotations, and I'm sure you'll find that one. It's an important one. How about this one? What's it going to give us? -11i, right? Because the square root of -121, the negative inside becomes an I outside, and that's just an 11, isn't it? The negative out front stays there. That's going to be a coefficient of our answer. Right? So we just get that. Okay? Make sense? No big deal. So let's look for some patterns of I. Now notice we see something going on here. So I is by definition equal to the square root of negative 1. It's just equal to I, right? I is I. I squared we already know is negative 1. I cubed we could break up into I squared times I using our properties of exponents, right? I squared is just negative 1, so that just becomes negative I. I to the fourth we could write as I squared squared, negative 1 squared, which is positive 1. But look what happens when we wrap around to I to the fifth. Well, we could write I to the fifth as I to the fourth, which is just 1 times I, right? I to the fifth equals 1 times I to the 1. Well, that's the same thing as I to the 1, right? I squared we could write, I to the sixth we could write as 1 times I squared. So do you see that we just get this one-to-one correspondence there? And every time I step up by, the powers step up by 4, I'm just going to be repeating this cycle. So what would I to the ninth be? What would it equal? Right, so what would the final result be? I to the ninth would just equal I. Yeah, because I to the ninth would go right there, wouldn't it? It'd go in that top row, okay? Well, we don't even have to make, and so we see that if k is just some whole number, I to the 4k to the power that's any multiple of 4 is always just going to be 1, isn't it? Right? We don't even have to be that complicated, though. Really, the way I choose to do this, I think, is you don't even need to worry about these other powers. All you need to remember is that I squared is negative 1. That's it. If I want to simplify what I to the 32 is, well, if I have an even power of I, can't I write that as I squared to a power? I to the 32 is I squared to what power? I to the 32, again, I to the 32 equals I squared to what power? 16, right? It's always going to be half of that original exponent, agreed? Well, I squared is what? Why did I do that? What's I squared equal to? Negative 1. Yeah, so what I've really got here then is just negative 1 to an even power. What's negative 1 to any even power? 1. What's negative 1 to an odd power? Ah, see the trick? So this is just equal to 1. Okay, how about I to the 89th? Now I can't do exactly the same trick because half of 89 is not a whole number, right? But I could split I to the 89th up into what two powers of I? Yeah, I could split it up into I to the 88 times my leftover extra I. And I to the 88th is an even power of I. So that's going to end up equaling negative 1 to what power? The 44, right? I'm going to get I squared to half of 88, which is just negative 1 to half of 88. So what do I end up with then? Negative 1 to an even power is 1 times I is I. Get the idea? Okay. So I to the 202. Well, tell me right now, I to an even power is always going to be one of two things. What? I to an even power. It's always going to be negative 1 or 1, right? Because I to an even power, I can always write as negative 1 to some power, right? If it's an even power of I, then it's going to be negative 1 to half of that even power, right? I to the 202 is the same as I squared to the 101. So that's negative 1 to the 101. Negative 1 to an odd power is negative 1. So you see the pattern? You always know if I have I to an even power, I'm getting one of those two results. What about I to an odd power? What do you think the two possibilities are? I or negative I. Yep, I or negative I, exactly. So I to the 55, how would I split that one up? What do I do with an odd power of I? Yeah, I break it up into I to the 54 times my leftover I. And so you can already kind of think ahead. What's the answer going to be? If it's I to the 54, what's that going to end up being? Is half of 54 odd or even? It is? Half of 54 is what? Oh, so it's odd. Okay, so what's the answer going to be? Negative I, yeah, right? Because you're going to get I to the 54 is going to break up into negative 1 to the 27. Negative 1 to an odd power is negative 1 times I, gives us negative I. Everybody see that? Okay, so it's pretty simple. Any power of I, regardless of how big, you can always simplify using one of those four patterns, one of those four strategies. Okay? I mean, they're all the same strategy, right? Oops. Okay, so what about that one? What's that equal to? What do you think? What do you think about that one? Anyone want to hazard a guess? What do you think? And what would you get? You get square root of 35 I squared, which is, what's I squared? Ah, okay. See, there's a contradiction here, isn't there? You're going to get, depending on how you approach this, you're going to get one of two different answers. If I just multiplied, there is a property that we've used a lot in the past. Haven't we just said this? The square root of A times the square root of B equals the square root of AB. That seems to tell us I can just make that the square root of 35, doesn't it? Okay, but remember, when we defined these properties, what kinds of numbers were we talking about? These were all properties of real numbers, right? Not complex, not imaginary numbers, right? So this one is, we can't depend on this in this case because is the square root of negative 5 real or imaginary? It's imaginary, right? So this, that pattern only works, that property only works for real numbers. So we have to first convert these into imaginary numbers with the imaginary unit I. So the square root of negative 5 just becomes the square root of positive 5 times I, right? Square root of negative 7 becomes the square root of positive 7 times I. And now, what if I multiply those four things together? Let's multiply them in a convenient order. Square root of 5 times square root of 7 is square root of 35. I times I is I squared. I squared is negative 1, so our answer is negative the square root of 35. Okay? So what's the moral here? You can't multiply negative radicands. You have to instead convert each negative square root to an expression with an I and then multiply the I factors separately, right? So you can now probably tell me pretty quickly what's the answer to that one going to be? Which is negative 7. Yeah. Right? I get 7I times I, 7I squared, so it's negative 7. Okay, how about this one? You might be, in this case it's not even going to make any difference, but you might be tempted to just combine those into one big square root, but what do I have to do first? Yeah, I got to get that I out of there, don't I? Right, before I do anything, right? So I'm going to take the I out of there, and then I don't think they showed this step, but once I do that, once I get the I out of there, I could combine those into one square root and simplify the fraction. You could just rationalize the denominator, but if I do that, I'm going to get a pretty darn big radicand inside that top radical. Everybody see that? That's going to be harder to simplify. So it would make sense to write this as I times the square root of 108 over 3, because what's 108 over 3? $36. Ah, that's a little better, isn't it? 108 over 3 becomes a 36. And so look what we get here. We just get I times the square root of 36. Well, that's just 6I, right? Okay, but you got to get the I out first. So yeah, it turns out that we've got this other superset of numbers called the complex numbers, into which all numbers fall. What do we know about the set of complex numbers? So complex numbers in standard form are always written like this: A plus B times I, where A and B are both real numbers. A is what we call the real part, and B, the coefficient of I, is what we call the imaginary part. Okay? So an example of a complex number would be something like 5 plus 2I. Okay? How would we graph this new set? Well, like this. If complex numbers have both a real part and an imaginary part, then in this infinite set of complex numbers, there are some subsets that we're familiar with. We're real familiar with this subset. All the real numbers, every number we've ever dealt with prior to today has been in this subset of the set of complex numbers, the set of real numbers. Well, what are real numbers? Real numbers are just complex numbers whose imaginary part is equal to 0, right? Every number you've ever dealt with is a complex number with a 0 imaginary part. We just didn't know it at the time. Okay? What about the numbers we've been dealing with up to this point today? Numbers like 6I. Those are what we call pure imaginary numbers because they have no real part. They're just an imaginary, just a real number times I. That's what we call a pure imaginary number. Whereas most complex numbers are going to have a combination of both. They're going to have a real part and an imaginary part. Okay, so dealing with these complex numbers. Now here's just another more sophisticated representation of how we could classify numbers into smaller subsets. Everything you've done in the past has fallen into this part, natural numbers, integers, rational numbers. There's another number called a real algebraic number that we haven't defined. In college you might talk about that stuff. And then there's a bunch of other types of numbers which involve complex numbers, and this can get very sophisticated. Okay. So one way that we can represent complex numbers really effectively is in the complex plane. And a lot of what you do when you're dealing with complex numbers revolves around using this complex plane. Well, what is the complex plane? Complex plane looks like the XY plane, and it acts like it in many ways, but it's different. The complex plane, instead of the horizontal axis being the x-axis, it's what we call the real axis, and the vertical axis, instead of being the y-axis, is the imaginary axis. When we take a complex number like 3 plus 2I, well, what's the real part of that complex number? 3, yeah. Okay, so the real part is 3. What's the imaginary part? 2. Not 2I, just 2. So if we want to write that as an ordered pair, the first component of the ordered pair is just going to be the real part, which is 3. And the second component, the vertical component, is going to be the imaginary part, which is 2. So where do you think we plot that point in the complex plane? Over 3 up 2. Okay? Make sense? So a lot of times, now we're not going to do this year. For this year, we're just going to represent the positions in the complex plane. But in future years, you're going to represent those complex numbers as vectors in the complex plane. Vectors are just like arrows. The tail of the arrow is going to start at the origin, and the tip of the arrow is going to end up at the point we just defined. And you can do all kinds of crazy things with these vectors in the complex plane. If you look at the rate at which, as you're if you write different types of coordinates, so you write, instead of writing things in terms of x and y components, if you write things in polar coordinates, where you're writing things in terms of angles and lengths of the vector, you can do some crazy stuff in the complex plane, like the rate at which you change the angle and the vector sweeps out area in the complex plane has a lot of meaning. There's some other, well, I might touch on a few other things later, but not too much. Just to give you a little, not that we're going to do anything with this on a test, but just so you have a little inkling when you see this in college what it's all about. Okay, let's practice a couple of these. These are super simple, but I just want you to get a little practice using these things. So what if, for example, you get a problem like this on the homework or the test. Oops, that's too big. They want you to graph the complex number -4 plus 3i in the complex plane. Well, where would I put that point? So I go left 4 and up 3. There you go. It's that simple, right? How about that complex number? Left 8 and down 3. How about that? How about that complex number? Okay, so look at that. A pure imaginary number sits on the imaginary axis. That one looks pretty familiar. How about that one? I'm going to make it. How about that? Right 5. So there it is on the real axis, which we sometimes call the real line, which you guys in the past have used a lot. You just called it the number line without knowing that there was this other axis there. You've always, going clear back to grade school, you've dealt with the number line, which is just the real line. That's all it is. Okay? All right, so we have to be able to do stuff with these complex numbers. It turns out we do a lot of, complex numbers play a really important role in math and science and physics and engineering. So we got to be able to manipulate these things and do arithmetic with them. Your intuition will tell you exactly what to do here. How do you think you add complex numbers? What do you do? Yeah, just add the real parts, add like terms. Just treat the I like a variable and add like terms. I'd add the real parts together, 4 plus 3, and get 7. I'd add the imaginary parts, 6i minus 2i, and get 4i, right? That's it. How would I subtract complex numbers? What would you do? Okay, kind of, yeah, but what, tell me the exact steps. What would I do? Distribute the negative like we would with a variable and add like terms. Exactly. So distribute the negative to that second complex number and then combine like terms and we're done. How do we multiply complex numbers? Well, you guessed it. So we're just going to expand these out like we would if the i's were x's, except we have to remember that powers of I mean specific things. Like if these were x's, we'd end up with a term that we just left as an x squared and be done with it, right? But in this case, we can't do that because I squared we don't leave that as I squared. I squared is equal to -1. So we would FOIL this out like normal. 4 times 3 is 12. 4 times -2i is -8i. 6i times 3 is 18i. 6i times -2i is -12i squared. But what does -12i squared become? 12. Anytime we have an I squared, that converts to a -1, and so it just flips the sign of that term, right? So we get that, combine like terms, and we just get a complex number. We always want to end up with, when we're doing adding, subtracting, multiplying, or we're about to divide, we always want to end up with a complex number in standard form, like that. A real part plus an imaginary part times I. That's what our answer needs to look like. Okay, so what do you think? Okay, actually, let's just jump up to here for a second. We'll jump up to, what do you think I'm going to do there if I'm dividing complex numbers? What's wrong with that right now? Yeah, I can't have an I in the denominator. That doesn't look like a complex number in standard form if there's an I in the denominator, right? Any suggestions how I could get rid of that? And the kind of thinking we did when we rationalized the denominator is going to be similar to this. What could I multiply the top and the bottom by to get rid of that I in the bottom? I could just multiply by I, couldn't I? If I multiply the bottom by I, I'm going to get 3i squared, which ends up being negative 3, right? That works. Okay, so it turns out that that's going to work. We're going to get, here, I'm just going to delete some of these things here real quick. That's going to work just fine. Oops, didn't want to do that. Boy, it took forever. Oh, okay, I guess I didn't have to do that. I could have just gone to that page. But what's the problem here? That's not going to work, is it? If I just multiply the bottom by I, when I distribute the I, I'm going to get an I squared there, which is good. That's going to make the i's go away, but I'm going to get an I attached to the 4, which doesn't go away, right? So I need a different strategy. So here's my strategy. Let's remind ourselves about what conjugate product patterns are. If I multiply two conjugates together, a plus b times a minus b, remember that when all the dust settles, I just get a squared minus b squared, right? The cross terms went away. Well, what if I multiply complex conjugates together? What are complex conjugates? Well, they're just two complex numbers that are conjugates, where the sign of the second term is positive in one case, so the real or the imaginary part is positive in one case and negative in the other case. Well, if I FOIL those out, look what I get. A squared minus a times b times I plus a times b times I. So those terms cancel, like always. What about that last term? I get minus b squared times I squared, which becomes a plus b squared, right? So the product of complex conjugates ends up, instead of being a squared minus b squared, it's a squared plus b squared. But that's helpful to us, isn't it? Because look what that does for a situation like this. What could I multiply the top and the bottom by? 4 plus 3i. Yeah. If I multiply the top and the bottom by 4 plus 3i, what am I going to get on the bottom? What's a in the bottom case? 4. What's b? 3. So what am I going to get on the bottom? I'm going to get 25. Yeah, 4 squared plus 3 squared, right? On the bottom. The top's going to be a mess, but the bottom's going to be easy. 16 plus 9 is 25. On the top, I'm going to have to do what we just did a little bit ago. I'm going to have to just FOIL them out, right? Distribute and collect like terms. But that's no big deal. If I distribute, if I FOIL it out, I get this final term with an I squared. 2i times 3i is 6i squared. What's that become? Negative 6. Good. And so that leaves us with, if I collect all the like terms, I just get that. 18 plus 26i, all divided by 25. Okay, is that technically written in standard form? What do I need to do to put this into standard form? Because standard form, remember, is this. Standard form is a plus b times I. I get two separate terms. So what could I do to that answer to write it in standard form? Yeah, I just split that common denominator. I split the fraction into two fractions. And we write it like that. Okay? Sometimes on your assignments, they're just going to expect you to write it like that. That's okay. I mean, if we do this, we just know in our mind that those really technically are split, but we're just writing it economically. Okay, makes sense? So you can pay attention to the instructions if they tell you to write it in standard form or if they just let you leave it like that. So if we go back one then, how about this case right here? So our trick is we always multiply top and bottom by the complex conjugate of the denominator. Well, this previous example, technically, what is the complex conjugate of 3i? If I write 3i as a complex number in standard form, what is it? 0 plus 3i, right? The real part is 0 plus the imaginary part is 3. So the conjugate of that, the complex conjugate of that is 0 minus 3i, which is negative 3i. So technically, I'd be multiplying by negative 3i over negative 3i. But if I do that, look what happens. I end up getting a 9 on the bottom, and on the top I get negative 3 plus 6i. And so then I've got to split those fractions and reduce each fraction. So what would have been maybe the very best thing that I could have multiplied top and bottom by? I is close. Negative I would be the best, wouldn't it? If I multiply top and bottom by negative I, why the negative? Well, that's going to make the bottom positive then when I multiply. Does that make sense? I'm going to get negative 3i squared, which turns out to be positive 3, right? So that would have been our most efficient way to do that. If the denominator is a monomial like that, just pick the easiest way to do it, right? If it's a binomial, like the more complicated case, then you have to multiply by the whole complex conjugate, top and bottom, okay? How are we doing on this so far? Is this all making sense? Okay. All right, so what's I to the negative 17? How would I deal with that one? Yeah, a negative exponent just puts it on the bottom, right? So I can just make this 1 over I to the 17, and I to the 17 you guys can deal with. See if you can do that one in your head. It's I to the 17. Just I, yeah. How come? Because it's I to the 16 times I, and is I to the 16 is an odd or an even power of negative 1? Even, right? It's I squared to the 8th. Okay, so I get 1 over I. Is that a good answer? What do I need to do? Can't have an I in the bottom. Yeah, got to multiply. Say it again. Well, okay, this one, in this case, it's not really rationalizing because that's not just irrational. It's not even real, right? But we have to make the bottom real. So we're going to multiply top and bottom by I or negative I. Yeah. Negative I is probably a little bit better because then what does that make the bottom? Positive 1, yeah, exactly. I get negative I squared, which is negative 1. And so, oops, darn it. Gives you that, right? Okay, so here's one of the reasons why these complex numbers, just one little glimpse of why complex numbers are so important. So if you were let's say you're wiring up an AC circuit, right? When you push current through a circuit, does the current just flow freely? No, it doesn't, right? Current doesn't. Only place where current flows freely is in a superconducting circuit, right? But you've never seen one and you probably never will. So in a real circuit, there's always going to be a little bit of impedance, meaning there's a little resistance to pushing the current through the circuit. Where does that come from? Well, part of it comes from just resistance. Like, you guys probably don't even remember these, but have you ever seen a regular old-fashioned light bulb, an incandescent light bulb, where you heat up a filament and right? I mean, those are like 15 years ago, every light bulb would have been an incandescent light bulb, but they use a lot of energy because those are the kind that get really hot, right? If you were to touch like a 100-watt incandescent bulb, you'd burn your hand. Most of the energy that's coming off an incandescent bulb is going to be heat, because when you push, the reason that it produces light is when you push current through that little tungsten filament, there's a lot of resistance in that. And so as the energy gets pushed through there, it heats up that filament so it glows really brightly. And it's that glowing, really hot filament that produces the light, but most of it's heat that's just lost that we don't even see. So that's a good example of resistance. If you put a piece of bread in the toaster, there's a lot of current going through that toaster because it's got to make the coils in the toaster really hot, which it does because there's a lot of resistance in those wires in the toaster, and they'll glow orange. So when we look at complex impedance, there's two parts to that. There's the real part, which is just resistance, which is the stuff I've been talking about. It's going to be the loss of energy due to heating up of the circuit, due to resistance. And that energy goes away and it's gone into the universe. And entropy in the universe increases and it's gone. There's another part though. There's another part of that which has to do with, it's called the complex impedance. And this comes from something a little bit different. When you push, like if you push electricity through a coil, like a spring, something strange happens. It's for complex reasons, the electric fields and the magnetic fields interact, and they cause that current to kind of slosh back and forth in the circuit. And that's called an inductor when you make like a spring-shaped coil like that. And so it's difficult to push electricity through that inductor because it keeps sloshing back and forth because of the field interactions. And so that's a complex part, or the imaginary part of this complex impedance has to do with that inductance or also capacitance. Anytime you have, like an ideal capacitor would be where you have two really big conducting plates that are flat that you're going to push up next to each other, and there's going to be a little gap that's either air or it's some dielectric that does not conduct electricity, doesn't conduct current. Because of the strong electric fields that are generated by this plate, there is going to be some current that flows through the electric field, and that current flowing back and forth also causes a resistance to pushing electricity through the circuit. Even if it's not technically a capacitor like that, there is a capacitance in any circuit just based on the wires, how close the wires are together and things. And so these other effects, look, they're attached to an eye. So this is really important. In many cases, this can be the biggest part of the impedance, might be the complex impedance. When you're dealing with wires like copper wires that conduct really well, usually the capacitance and the inductance are more significant than what we call the resistance, right? This other part we call the reactance. But the resistance, the electrical, the dissipation of energy through heat is really minor in copper because it's such a good conductor. So this becomes a big deal, right? It becomes a really big deal. And so if we wanted to, like for example, if we wanted to calculate the complex impedance in this simple circuit right here, right? This is a serial circuit where all of the circuit elements are in a row, they're lined up. So the current has to go through each one of those circuit elements in order, right? Well, what are the three? In any analog circuit, there's only three kinds of circuit elements. You have resistors, which are things that dissipate heat. There's some resistance. You have inductors, and notice they look like a coil. And then you have capacitors, okay? How do we account for their impedance? How much they're going to make it difficult. How difficult are they going to make it for current to flow? Well, the resistor, if it's and by the way, ohms are the measurement of impedance. That's the unit for impedance. If we have a 3 ohm resistor, well then that means the impedance is just 3. It's just going to be the real part of that. It's just 3. If we have an inductor, it's different. If we have a 5 ohm inductor, the impedance is 5I. And if we have a 6 ohm capacitor, the impedance is negative 6I. So if I wanted to add up the total impedance in this circuit, it'd be easy to do. That's a resistor. So what's going to be the contribution of that resistor? 2. Good. So this guy is contributing 2. How about, or sorry, that's not 2, that's a capacitor. Sorry, messed it up. The capacitor, what's going to be the contribution of that 2 ohm capacitor? Negative 2I. How about the 8 ohm resistor? 8. And how about this 4 ohm inductor? Yeah, so if I add all those up, what do I get? Eight plus 4I minus 2I. The complex impedance, Z, is just 8 plus 2I. Okay? So it's a complex number. Now, how do you know how big that is? Okay, this is something kind of cool. When are we out of here? 55? Okay, so yeah, I've covered everything I need to cover. We'll go through a little bit more. I've got a few more cool things to share with you, but this is kind of cool. So if we go back to this complex plane. So the distance from the origin is what we call the modulus of the complex number. If a number is on the real axis, like for example, if I have that number right there at positive 4 on the real axis, how far is that from 0? 4. How about this one right here? Well, how far? But if it's a distance, it's always it's 5. So that looks an awful lot like absolute value, doesn't it? So the modulus of a complex number on the real axis, we just call the absolute value of that number. But it turns out that distance is dependent on both the real part and the imaginary part, right? If I want to figure out the length of that vector, I'm just going to use the Pythagorean theorem. The horizontal leg of that triangle is just going to be A, the real part, right? The vertical leg is just going to be B, the imaginary part. And then what's that tell us? That tells us that the impedance squared is just equal to A squared plus B squared, right? So the modulus, the distance then, we write as the square root of Z squared, which is the square root of A squared plus B squared. Just the length of that hypotenuse, right? So if I wanted to actually know, for example, how much, like that's kind of a weird answer, this answer that we just got for this circuit. 8 plus 2I, is that big or small? Who knows, right? But if I calculate the modulus, which we write like that, that I can relate to. The square root of 64 plus 4 is the square root of 68. That means something, right? Square root of 68 is something like, well, what is that? That's roughly like 8.2-ish, a little less, right? Okay. That tells me something. About 8.2 ohms is what the complex impedance is going to be, right? That make sense? Okay. Now, what happens if you have a parallel circuit where I have multiple branches for the current to flow through? Then we do something like let's take, for example, this C. Current, it's going to travel from the battery around the circuit. It could go through that conducting path, or it could go through that conducting path. I have to calculate the complex impedance of each of those two paths. I'd call this one Z1. The impedance of that first path is Z1, which I could calculate. You guys know the tricks, right? We could calculate the impedance of the second path as Z2, and then the overall impedance of the parallel circuit is going to be the product of the path impedances divided by the sum of the separate path impedances. And so we're going to end up having to do some arithmetic. We have to multiply complex numbers, and we're going to have to divide complex numbers to come up with a solution on this one. I gave you one like that on the homework. Your last problem is going to be you got to actually calculate the complex impedance of something like that. So have fun. I'll put the assignment up.